All right, welcome back. 11.6, we're not actually going to be doing 11.6 in the book. We kind of got our own 11.6 to do. So let's talk about linear factorization and polynomial division. This worksheet or note sheet, whatever you want to call it, the PDF file is available on Schoology. So you should make sure you go ahead and get that. And yeah, we'll just kind of work through these notes kind of like how we used to in class. So first of all, we're going to talk about polynomial division, the long division. So this is very similar to long division like with numbers, except now we're just doing it with polynomials. So basically, we're taking x squared plus 10x plus 21, and we're dividing it by x plus 3. So x squared plus 10x plus 21 is being divided by x plus 3. So essentially what we want to do here is we want to kind of look at the variables and say, okay, well, how are we going to make this x into an x squared? Well, we would need to multiply it by x. Okay? And then we go ahead and we multiply that. So we multiply down, so x times x is x squared, and x times 3 is 3x. Now, just like regular long division, what we're going to do is we're going to subtract this, and we're going to subtract the whole thing. So that's kind of important to remember. We're subtracting this whole thing. And so the x squares will cancel. 10x minus 3x, we got 7x. And then we want to bring down the rest of the problem. And so again, look at the variable, look at the first term part. That's an x, by the way. How am I going to make this x a 7x? Well, I'd have to multiply it by a positive 7. Okay, and then go ahead and multiply it. So 7x plus 21, and we subtract. And there's our remainder. So this one divides evenly. And so we have a remainder of 0. Okay, so it's going to be important to remember that that last part is the remainder. So this is equal to x plus 7. Right, so if you take this and divide it by x plus 3, we get x plus 7. That's our answer to the division problem. Okay, so let's go ahead and try another one. So we got 12x squared plus x minus 4, and we are dividing that by 3x minus 2. So how are we going to take this 3x and make it a 12x squared? We would multiply it by 4x. Okay, and then we're going to go ahead and do that. 12x squared minus 8x. And we subtract the whole thing. So here's where we got to make sure we're doing this correctly, because now we have x minus a negative 8x. So what we're going to have is we're going to have 9x. Okay? Because minus negative. Bring down this minus 4. Again, how are we going to do that? We're going to need a plus 3. So that's 9x and minus 6. And we're going to subtract, again, the whole piece. And what we'll be left with is a 2. Now, at this point, we don't have anything else to bring down, to drop down. And we are of less degree than what we're dividing by. Okay, because this one has an x term, and what we have left doesn't have an x term. And so once we get to that point, we're done, and this is our remainder. So a couple different ways we can write this answer. The sort of shortcut method of writing the answer, it's not really an official way of writing it, would be to write like 4x plus 3 with a remainder of 2, right? And you just kind of like do remainder 2. Or the actual way of writing this would be to show that we have, so the answer would be 4x plus 3, and then there's still this 2 left when we divided by 3x minus 2. So plus 2 over 3x minus 2. Okay, because that's what a remainder is, right? If you're dividing by whatever number, if you're dividing by 7 and you get a remainder of 2, you essentially have 2/7 left. Okay, and so that's kind of what we do there. We put 2 over what we divided by. Right? And here's another example. I would have you guys probably pause this, do it by yourself first, and then check in. So I'm going to set this up. We got our polynomial here, and we're dividing it by x minus 3. And I'm going to need an x squared here to get x cubed, and then minus 3x squared. And then subtracting, I would have 7x squared. Bring down what I got here. And continue the process. So it looks like I would need a 7x. So 7x squared minus 21x. Subtract. So that would give me 16x. Down to 5. So it looks like I would need a 16. So 16x and minus, what would that be? 48. Let's make that look like an 8. And subtract those. And so it looks like 53. There we go. So we have a remainder of 53. And so our answer to this problem is x squared plus 7x plus 16 plus 53 over x minus 3. All right, so we have a remainder of 53. So whenever we get a remainder, it means that what we've divided by doesn't actually divide it evenly, right? It's not divisible by this linear factor. And that's going to be part of our linear factorization. So essentially what it means is if you're finding that there is a remainder, right, if there's something left over, then what it's saying is that this is not actually a factor, right? Because if I try to factor x minus 3 out of this polynomial, of this third degree polynomial, right? If I try to factor x minus 3 out, I won't be left with any nice factors left, right? It can't be factored out of it, essentially, because there's a remainder. Whereas in this first example, x plus 3 is a factor of x squared plus 10x plus 21 because I got a remainder of 0. Okay, and that's part of like the remainder theorem there. So if we get a remainder of 0, then we know it's a factor. Okay, so that's long division. Now what we're going to talk about is something almost exactly the same. It's called synthetic division. When we can use synthetic division is when we're dividing by a linear factor whose coefficient is 1. So it's very useful for linear factorization. It's very similar. It's the same essentially as this, but it ignores a lot of the pieces and just uses the coefficients, which is essentially what we're doing. It's just some people like it better. It seems like a simple method to do. So for example, we're taking x squared plus 5x plus 6 and we're dividing by x minus 1. So here's an example of doing that with long division, okay? And we would have x plus 6 plus 12 over x minus 1. We see that we have a remainder of 12, okay? So here's how we do synthetic division. The first step is we write down the coefficients, just the coefficients, in order. So it's got to be in standard form, descending degree, and we have to remember to put all of the coefficients, including any 0 coefficients, like if there's a missing term. So for example, if we go from like x to the 4 plus x cubed, and then we jump to plus x. Well, we've skipped over x squared. So we have to put a 0 in for that place. We have to have everything in order, okay? So here's the steps. We write the coefficients down. So for example, here we see the coefficients are 1, 5, and 6, right? So there's nothing missing. It went from x squared to x to the 0, right? Nothing. So 1, 5, and 6. Then what we do is we put the 0. It's important to remember that it's the 0 there. So x minus 1 is the factor. So x equals positive 1 is the 0. So we put that on the outside. Okay, and we kind of use this upside down division bar. And now we just go through this process of essentially what we do in division, but it's just like a neater process. You don't have to keep a long string going down. So you bring the first term or first number down. You just bring that straight down, okay? And then what you do is you multiply. So this 1 times 1, and you write the answer right under the next coefficient, 1. And then you add them. So 5 and 1 is 6. And then you do that process again, multiply. So 1 times 6, 6. So you put the answer there. And then you add them, and you get 12. Once you're down to the very last thing, right, this last number that you get is your remainder. Okay? The idea here is that if that last number is 0, then we have found an x-intercept. We found a 0, or we found a linear factor. Let's try some. So let's go ahead and practice this. So x cubed plus 4x squared minus 5x plus 5, and we're dividing by x minus 3. So the first thing I'm going to do is I'm going to write down the coefficients. So I got 1 and 4 and negative 5 and 5. And I'm going to be dividing those coefficients by a factor of x minus 3, and so the 0 I'm going to put out there is 3. Okay. First step is bring down the 1. And now multiply. 3 times 1, 3. Add. So now I got 7. Multiply. 21. Add. 16. Multiply. 48. Add. 53. Okay. Now, those numbers might sound familiar to you. We have done this same problem using long division. So if you go back, that's this problem we just did, right? So those numbers were in here somewhere. They're like in the answer, in the work, okay? And what we got to remember with synthetic division is if we're dividing by a linear factor, we're dividing by a factor that starts with an x. We're taking a third degree polynomial and we're dividing by a first degree polynomial. Essentially x cubed divided by x. Which means what we get, what we're left with, is always 1 degree less than what we started with. Okay? And so what we have here is the first term is now 1 degree less than we started with. So this is the coefficient on x squared. And then it goes in order. So plus 7x plus 16. And then there's our remainder. Okay, so there's synthetic division. So I would say go ahead and try this one and be very careful of the missing term here. So what that means is when we go to list our coefficients, the first coefficient would be 1, and then negative 4. And then it jumps, right? We skip an x squared term, which means technically speaking, it's 0x squared. And then minus 9x, so minus 9, and then a positive 15. and we are dividing this by x minus 3, so the 0 is 3. And so let's go ahead and try this with synthetic division. So bring down the 1, multiply, add, multiply, add, multiply, add, multiply, negative 54, I believe. And then add these. And what do I get here? Negative 39, I think. Sure, that works. So 1 degree less than what we started with. So this is x cubed minus x squared minus 3x minus 18 minus 39 over x minus 3. And that would be our answer. Okay? So that's synthetic division. So what we would use synthetic division for is to find the zeros, or essentially to find the linear factorization, which we'll go over in a second. So first, let's talk about finding the zeros. Remember, if that last number is a 0, if there's no remainder, then it's a 0. That's what we're looking for. So the first thing we want to do is we want to kind of identify a 0 that we can test. So we could just kind of go through a bunch of them, try and figure it out, or we could use our calculator to find the first 0 to use and then go from there. Or we can kind of just look at the coefficients. Right now, if I see the coefficients, I see a negative 20, positive 11, positive 8, and a positive 1. That actually adds up to 0 right now, right? 1 plus 8 plus 11 and minus 20 would be 0. Which means if I plug 1 into all those x's, I'm essentially just using the coefficients. And so it looks like 1 will work as a 0. So I'm going to put the 1 on the outside. And then I'm going to put the coefficients, the 1, the 8, 11, and the negative 20. And we're going to test to make sure this 1 works using synthetic division. So bring this down, multiply, add, multiply, add, multiply, add. So that last number is 0, which means this worked. This is a 0. This is the remainder theorem. This is a linear factor, or, well, x minus 1 would be a linear factor. Positive 1 is the 0. So seeing this, I can now say, I'm trying to find all the zeros in this problem. Seeing that the remainder is 0, I can now say that x equals 1 is a 0. Okay? And what do I have left? 1 degree less. So this is x squared plus 9x plus 20. Okay? From here, we can go ahead and do this again. We can try to figure out another 0 term and do the synthetic division again. Or once you get down to a quadratic, you can use your factoring, right? We can just factor this normally. So this, I would be looking for numbers that multiply to 20 and add to make 9. This factors into x plus 5 and x plus 4. Okay, and so I know that my other zeros are negative 4 and negative 5, and there's my answers. So that's essentially what we're going to use synthetic division for. Okay? So linear factorization. Linear factorization of a polynomial is when you write the polynomial as a product of as many linear factors as you can. So, for example, you just have like a string of parentheses next to each other. It's basically factored form, right? We can think of this as just writing it in factored form. Okay, so we're going to find the linear factorization of this polynomial, right? It's a fourth degree polynomial, and we're going to identify the zeros from the factorization. So first thing we're going to want to do is let's try and find a zero. So whether you're going to plug that in your calculator and just find a zero first, kind of get you started, that's fine. Or if you want to maybe, I like to check ones and negative ones because it kind of seems like it's the easier ones to check. So if I check the coefficients here, I have 20, a positive 1 and a positive 1, that's positive 22, and then I see negative 21 and negative 1, so that's negative 22. So if you notice what I'm doing there, I'm just checking the coefficients, and all the coefficients add up to 0. So if I just plug a 1 in, that doesn't change any of the coefficients, and that's all I need. So let's do synthetic division. Here's my coefficients. Check to make sure nothing was skipped. Nope, that was good. And I'm going to put a 1 on the outside. I'm going to go ahead and do this synthetic division. And it does indeed work. So now what I'm left with is a cubic, but I can just keep going here. Okay, I can keep going. So now let's see, if I add these up, it won't add up to 0, right? But I can try another value on the outside, and what I notice is that these are quite close. I'm just going to go ahead and try negative 1 because negative 1 can sometimes change signs on certain things, which can lead to balancing things. So I'll try negative 1, and remember, if I get a remainder of 0, then it worked. It's a correct factor. It's a correct 0. So let's go ahead and do this. So 1, multiply, add, multiply, add, multiply, and add. There we go. We got that to work. So now we are left with, now I've gotten down to a quadratic, which is what I wanted. So x squared plus x minus 20. So can I factor this now further? Numbers that multiply to negative 20 add to make a positive 1. So x plus 5 and x minus 4. Okay, now these are also, those are my zeros. So what factor is that? So if this is a 0, this leads to a factor of x minus 1, and this one leads to a factor of x plus 1. And so if I put those next to these, now I have the complete linear factorization of this function g of x. Okay, there's the linear factorization. So it's the exact same thing as this function, but it's essentially in factored form, right? Linear factorization. It's a bunch of linear factors. And so now I can identify the zeros as x equals negative 5, x equals 4, x equals 1, and x equals negative 1. Okay? That's linear factorization. So when we are finding zeros, we're essentially finding x-intercepts, which means we want to know when it crosses the x-axis, right? However, we know that we can have a function that doesn't necessarily cross the x-axis anywhere, but we could still solve it using imaginary roots. So when we're solving equations, we are interested in the imaginary solutions. So we will need to find those imaginary solutions. We'll do that using the quadratic formula. So here we're going to solve x to the 4 minus 6x cubed plus 22x squared minus 30x plus 13 equals 0. We're going to solve this equation. So we're going to start with synthetic division. Okay. I'm just going to, again, kind of look at these and see if I can just test some values. So I'm going to start with 1. Sometimes -1 works. Let's go ahead and start with those. So I'll start with 1. And my coefficients are 1, -6, 22, -30, and 13. And so let's do our synthetic division. And that works correctly. Good. So a remainder of 0. We know that x equals 1 is a solution to this equation. It's not the only solution, but it's one of the solutions. X equals 1. Okay, so now looking at what I have left, because right now I'm only down to a cubic, right? I started with x to the 4th. I did 1 round of synthetic division, so now I'm left with a cubic. So can I continue this further? If I look at these coefficients now and add them all together, it looks like they add up to 1 again, or sorry, 0 again, which would mean that 1 should work again. So if I do that again, let's see if this works again. So this would be -4, and then -4, so 13, and then 13, and then 0. Yeah. So that works. So now what I've done is I've gotten down to x squared minus 4x plus 13. Okay, and now what we can see is that there are no numbers that multiply to 13 and add to make -4. So this is where we would now use the quadratic formula. Okay, so by the way, since 1 worked twice, essentially what we have here is back to that idea of multiplicity, right? That's a multiple 0 at x equals 1. So that's kind of like saying x minus 1 squared, right? Because of the multiplicity, because it happened twice. So x minus 1, right? Okay. And then to finish that thought, that would be then times x squared minus 4x plus 13, right? So here are the real x-intercepts. There's only 1. It's a touch and turn because it's multiple. But since we're solving this equation, we're going to go ahead and find the imaginary roots using the quadratic formula. So I know that my a is 1, and my b is -4, and my c is 13. And I'm going to plug that into the quadratic formula. So -b plus and minus x equals, of course, -b plus or minus the square root of b squared minus 4ac, all divided by 2a. And so we get 4 plus and minus the square root of, let's see what this should be. Swap over my calculator here. So we have 4 squared minus 4ac. And we get -36 under the square root sign, which is what we expected because we were expecting imaginary roots. Divided by 2. So what is the square root of -36 using imaginary numbers? Well, we can take the square root of 36, it's just 6. But what's the square root of the -1? Well, that's going to be I. Okay, go ahead and divide by 2. We get x equals 2 plus and minus 3i. And that would be the imaginary roots. So the solutions to this equation are x equals 1, happens twice, and x equals 2 plus 3i, and x equals 2 minus 3i. You don't have to split the plus minus sign if you don't want to, but I'm just showing you that those are two different numbers, remember. Okay? There's solving for imaginary solutions. So now what we're going to talk about is we're going to talk about going in the opposite direction. So suppose we're given the imaginary roots, or any root for that matter, which we've already done, but so now we're adding the imaginary roots, and we want to write a polynomial from that. So let's take a look at these examples. Find a third degree polynomial function, f of x, with real coefficients that has zeros at x equals -3 and x equals I, and such that f of 1 equals 8. So the real coefficients part, that just means that we can't leave I in our polynomial. Okay, we have to get rid of that somehow. So what we're going to do is, let's go back to just, let's ignore the x equals I for a second. If I tell you that the 0 is at x minus 3, what does that tell us? It tells us about the factor, right? It tells us that x plus 3 is a factor. So, okay, how do we know that? Well, essentially, what we're doing is we're taking this and, not that, we're taking this, the actual thing that they give us, and we're going back to setting it equal to 0, right? So I would add 3 to both sides, and I'd get x plus 3 equals 0, and so that's my factor. So that's what we're going to do with this piece. Okay, but the first step we're going to do is we're going to get rid of the I. So how do we get rid of an I? Well, we square it. So what we have to do is we have to square both sides. So x squared equals, what's I squared? -1. Okay, now do this idea where we just set it equal to 0. So add 1 to both sides. And there's my factor. And so that's what I get. There is a coefficient as well. Okay? And so now we're going to use this information to find what that coefficient is. And so 8 equals a times 1 plus 3 and 1 squared plus 1. I'm just plugging 1 in, and I know it has to output 8. And so 8 equals, that's going to be 4. That's going to be 2. 4 times 2 is 8. And so a equals 1. Okay, and so our function is x squared plus 1. That's a squared. X squared plus 1 times x plus 3. I like to just kind of write the highest degree out front. Not really needed, but is this a third degree polynomial? Because I only see 2 sets of parentheses. Is this a third degree polynomial? Yes, it is, because this is an x squared term. So there's 2 right there and an x there, so there's our 3. All right, so go ahead and try the next one and pause the video, finish it, and check your answer when you're done. So 4th degree polynomial, and we have x equals -2, 2, and 3i. So I know that that's going to mean that f of x equals a, there's my coefficient, remember, and then x plus 2, x minus 2, and then I'm going to do a little side work over here. So I have x equals 3i. So square both sides. X equals, so it would be 9 and -1, so -9, x squared. And so x squared plus 9 is my other factor. So there's what we got there. So now we put 240 equals a times, I'm plugging 3 in. And so 240 equals, let's see, that would be 5 times 1 times 18. So whatever 5 times 18 is, what's that? 50 and 40, 90? Is that 90, I think? 90A. Now divide. 240 divided by 90. 240 divided by 90 is 2.6 or 8/3. So A equals 8/3. So my function 5x f of x equals 8/3 x squared plus 9 x plus 2 x minus 2. There we go. And that is it for 11.6. So we talked about linear factorization, finding imaginary solutions, synthetic division. Yeah, a lot of good stuff here in these notes. So hopefully you follow along with the PDF. If you have any questions, let me know. Don't forget to drop into my office hours. There will be a homework sheet because we're not working on this book currently. So there will be a homework sheet on 11.6, and then technically we're done with chapter 11. So I've posted some chapter 11 review problems. Those are out of the book. And yeah, that'll be it for this week. All right, I will see you guys later.